All right, so I'm going to demonstrate how to use GoldSim to um, calibrate a model. Um, the purpose of this presentation is to show you methods and techniques on how to do a calibration within the GoldSim framework, and I can't guarantee that we will accomplish a good calibration in this model. I just built this. It is using real data. It is for a real site, but I haven't had time to work on it long enough to um, come up with a very good calibration. But I will show you the techniques that I'm using. One thing that I do want to show you is where the site is located. So let me open up a map here, and as soon as let's see, I just need to go and open. Here we go. Bringing that over. Okay, so this site is located in the state of Utah, near Salt Lake City, and hopefully all of you can still see that okay. Yeah. All right. So I've delineated this watershed using Google Maps. You can see here outlined in red, and I'm going to now zoom in on the watershed. These different colors represent elevation bands, and that's what is used to simulate snow accumulation and melt for the model that I am employing for this task. And we have in our library we have three different snow model techniques. This one that I'll show you today is incorporated in a model called GR4J runoff model, and it can be used within other. You can combine it with other models instead of GR4J, but um, it can work as a standalone model to simulate snowpack and the melt process to help you with watershed runoff in um, a snowy area. So what we have here, these elevation bands that are a way to discretize the model. Um, it turns out that this is showing four different bands. In the model I have, I decided to go with just three, so it's been adjusted a little bit. But um, essentially what you do is you just follow the contour lines at different elevation zones, and call these bands that we represent snow accumulation for the zone that bounds the upper and lower portion of each of these bands. So for example, at the top end, we have the highest elevation is this kind of yellow orangey color. Um, that band would be represented as a lumped model within the framework of the snow model overall. So it's important to delineate the watershed in this way. And also I've found that um, adding in this size of a watershed, this is about 30 square kilometers. I didn't see any benefits of going to more than three zones, and it just adds more and more complexity, right? As you add more zones there. I didn't test less than three, but that could be done too. So it is important though to separate it into zones though, because obviously you'll have much more snowpack in the upper elevations. In the lower elevations, perhaps very little. So that's the reason why we do that. It also turns out that there is a snow gauge located in this watershed. It is kind of mid level, a little bit in the higher elevation area in this watershed. And we also have a river flow gauge at the tail end. So it works out perfectly for building a model to calibrate. Also, at the snow gauge, they are monitoring not only snow depth, but also snow water equivalent um, and temperature, min-max temperature, daily min-max temperature. All of the information I'm using for this model are daily values. Um, and also precipitation, total precipitation. Okay, so that is the site I'm looking at. So what we have here is essentially 3 components that I've added to the model. We have this one called Simenage, I guess. I don't really know how to say it. This is a French based model. GR4J is originally all programmed in, it's all documented and programmed in French. But there is, in the model, I have links to both the French documentation and there's English documentation now online there. Also, if you open the note pane, this is where I put the documentation. So if you click on the container, you can see the documentation there for these models. I'll go ahead and turn that off for now. Okay, so what I have done here is I've put in the observed daily precipitation totals, daily maximum and minimum temperatures, and then the observed stream flow at the downstream end. And, oh, let's see. Somebody asked, how did you delineate the elevation bands? Oh, sorry, I kind of glossed over a lot of that stuff. So I just did it manually. It was because it's such a small area, and this was a long time ago actually when I worked on this. But I just have contour lines, right? So in Google Maps, I just turned on the contours and I just followed the contour lines generally. I mean, I didn't follow exactly, but I just kind of, you can see that the lines are kind of, jagged because I only put a few vertices in. I didn't follow exactly, but I realized that there are tools out there today where you can automate this kind of process and that, but it didn't take very long, right? To just quickly draw these polygons, just following, you can just zoom in and just draw these. Google Maps has a feature called My Maps, where you can draw polygons and color them. You can draw lines and polygons and points and all that kind of stuff. So pretty straightforward. I was just doing it so that I could calculate the areas, because the nice thing about the polygons in Google Maps is you can calculate their areas. So that's how I did it, to answer your question. Okay. Anyway, so let's go into I just want to review the model. I didn't want to make this presentation so much about the model itself, although it is important, but rather how I'm going about doing a calibration, some of the ideas. Also, this is the second time I've given this presentation. I already did this a couple of days ago, and one of the questions was, there's a few questions. One of them was asking about adding a different calibration techniques, and certainly we can, and I'll show you one that I added since then. But let's start with just the basics of the model. So the snow portion of the model, turn the notes back on, the snow portion of the model here, if I go in, then what I do is, because this is coming from our library, I just put in placeholders. These are just expressions that just reference where the data is coming from. So the point of this model is that it should be able to be just copied and pasted. Plug and play is kind of the idea here, where you can just copy this whole container, everything in here, and paste it into your model, and then just link up the data sources to these expression elements. That's why I put them up here at the top. This is where the data is coming from. If I go back up a level, so I'm using the navigation. This is like an address bar up here. I'm using that to navigate. You can also use the browser right over here to navigate in the model, or, well, there's multiple ways. Or I could just click on the little red arrow to go in, right? But anyway, so my data is coming from here. So then I go into the model, and then I have these here, but there's also mean temperature that it needs. So that's a calculation. which is min plus max divided by 2 in my case, but you might have data that's just mean temperature data too, right? So you could link to that instead of just calculating it. That would mean you would at this level, you would have 3 temperature time series there. Anyway, next you go into elevation adjust container, and in here is where we make adjustments for the different elevation bands that we are using. So it's there's this element here, hypsometry. So if we go in here, then we put in the mean elevation of each of those bands. The entire model, the snow model, is in metric, right? So you could enter these in as feet, no problem, right? So if that's what you have, then you could come in and say, okay, my mean elevation, for this one right here is, I would need to, I need to go back to the contour view. But anyway, we could enter these values as feet, and GoldSim just converts it because the display unit here is set to meters. So it could take feet or meters, no problem. Okay, so those are the 3 different elevation bands that we have, and then we have a reference elevation, and this is the elevation of the gauge, so where we are measuring the temperatures. And we are measuring the temperatures up at the SNOTEL site, which is up at high elevation. So that is these 2 elements are super important for the snow model. So you need to make sure those are correct because it's using a temperature lapse rate that says, the temperature should be changing as you rise in elevation by some amount. And so obviously that would be a big driver in the model. Also, same thing with precipitation. Okay, so once those adjustments have been made, we're essentially kind of splitting these inputs into 3 different values for each of them, right? For the 3 different elevation bands, and then those all play a part as we accumulate and melt the snow. And then after that's all done, we still have these, we account for snow for these 3 zones as it's going along, and then at the end of the model, we are then essentially summing. We take the mean of the 3 zones for both the melt rate and the rain, take the mean, and then we add those 2 together for the rain only and the snow melt to come up with just one number. So that's how the model works. But from these elevation bands, then we come into, let's start with the partition snow rain. So we need to, based on the temperature, we need to decide whether the precipitation is snow or rain, right? So there's going to be a split in there. So if I come in here, then we have the split that says, okay, here's the rain component and here's the snow component. And we do that by looking at the elevations. So if I open up this, you can see, without going into a lot of detail, the very first if statement here is if the elevation, and we're doing this for 3 different elevation zones, right? This is, you can see that this expression is a vector of this thing called elev_zones. We can go look at that. That's an array label set. So I go up here to model, and then I go to array labels, elevation zones 1 through 3. Okay, so this element will have 3 outputs as it goes along through time. And what we have in here is what's called a vector constructor. So these are important in GoldSim. These allow you to, on the fly, generate immediately an array. And so as it generates it, you can refer to an internal parameter called row right here. This is an internal parameter that is built in and it can only be used when you have a vector constructor or a matrix constructor, either one. Vector in GoldSim, right, is just one dimensional array. Matrix is a two-dimensional array. So a vector constructor allows you to say, okay, for each row, I want to iterate. I want to iterate over the array, each item of the array. And as I walk over that, I will assign the row value starting with 1, and then go to 2, and then go to 3. So for hypsometry with a bracket 1, imagine this says 1 right here, then that would be the first elevation zone. And it does this calculation. It says if we are less than 1,500 meters, blah, 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 do all this thing. So that's how the vector constructor works, and that's how we walk through each of the zones as we do these calculations. And then we split up the snow and the rain, and then the snow gets accumulated here in the snowpack. The rain just falls through. Okay, so it's really important to understand that this model is just calculating the input for what we would use to calculate runoff, which would be the input for a runoff model. So this, what we're calculating right here is not the runoff from the watershed, right? This is similar to rain, but it also includes the melt, right? So there's the delay of when the snow, the precipitation is held up into the snowpack, and then it comes down later. So that's really all that this is doing. It's kind of delaying a portion of the precipitation amount by storing some of it and then releasing it later. Okay, so the kind of the crux of all of this is in this container called melt rate. If I go into here, then here's where we have a few things. First of all, there's this really important output called snow critical depth, and we're using a script element to calculate this. This is actually thanks to Dave Hoekstra at, you know what, I forgot where Dave Hoekstra is working, sorry, but Dave Hoekstra has been helping me, and I will note his name when I post this on our website. This used to be something that was a lot more complicated, but he put it into the script, which is very helpful. So what it does is it says at time 0, before we run the model, let's just, we have observed records, we have the time series already available to us. Let's just go through all of those observed records and let's calculate some things. For example, from the historic record, what would be, for example, the average precipitation? What would be the average temperature? Things like that. But the important thing that we need from this is the critical depth of snow. And so we calculate that from the observed record and come up with a value before the simulation even starts. So that's a nice thing about a script element, is you can kind of do a pre-processing. You can also organize calculations in more of a script format instead of using gold sim elements. But anyway, this is only calculated one time, and it's at the very beginning, is at time 0, at E time 0, elapsed time 0. All of these other things are occurring as we walk through time. Okay, so we have in this case, this is the temperature of the snowpack itself that is calculated, and you can see that it doesn't have any units here because there are calculations in here that these are empirical calculations that are essentially unitless. So we had to strip off the temperature units there to do the calculations, stripping them off as Celsius, because this is a metric based model. So sometimes these kind of things have to be done. It's not recommended in your day-to-day models that you remove units, but in some cases where you have techniques like this that are unitless equations, we need to take the units off, but then just make sure that they're applied later if they're needed. Okay, so from that we get a melt potential, and then we can calculate what the actual melt will be. So these are all hard-coded equations that are just part of the model. We don't change these parameters here. The parameters that can be changed are these data elements. So for example, this one called degree day factor, this is a very important parameter for calculating melt, and it is one that can be used to calibrate the model. Okay, so with that melt rate, then we apply that to the snowpack, and we're using a reservoir to account for snowpack here. Oh, somebody asked, uh, thank you. Also, somebody mentioned Dave Hoekstra is at SRK. That's right. SRK is where Dave Hoekstra is. Thank you. Somebody asked, are scripts always at the beginning of the causality sequence, or does it depend on how it is written or used? Okay, that is a really good question, and I would require that I mention the causality sequence. What is the causality sequence? So to view the causality sequence, you go to Model, and then causality sequence, or type the F10 key. And what this shows you is the sequence of calculations as you walk through the simulation. So on each time step, this is the order in which the calculations are occurring. And you can view the order of the calculations within a single container at a time by going up here and clicking on a container, or you can see the order of equations for the entire model at once. So the question is, in the case of a script element, where does this get placed within the context of all the other calculations? It actually depends, and GoldSim automates that process of figuring out what goes before what. And it turns out that because the script element is a function of things, there are, if I open this up, there are things in here that is referring to outside of the script element. So for example, this one here called precip gradient in this equation, precip gradient, it's a function of that. So it must fall in line in the causality sequence after that element, and any other element that is referring to outside, like this one and others. So it would just have to fall in line after that. I could highlight this element and type F10, and then it will show me where it falls into place right here, number 11. It is pretty early on, but the question is probably being asked because I'm telling this to only run at the beginning. Well, it turns out that this element, I'm pretty sure, is running mainly on input data. Let's see if I go to a function of, then I can see all the things. So there really isn't anything in here that's a function. I can't expand this list any further. So we would expect this script to be near the beginning of the causality sequence in which and that's where it is. I'm not controlling myself. I'm not putting it anywhere else. But the really important point here of the script element is this one line I put in here. This is actually something I added later. The way that it was originally built is it was put into a container that has a trigger that says, only activate at time 0. That's one way to do it. Or you could put an if statement inside the script that just says, if E time, now this is E time, right? E time is elapsed time of the simulation. If E time is 0 days, then go ahead and walk through this process and calculate these things. Otherwise, don't. And this is really, really important to do this kind of thing. If you only need it if it's just a one-time thing, in this case it is, I don't need to recalculate this as we walk through time in the simulation. I just need one number at the very beginning of the simulation. So I put this if statement here so that this will, essentially everything in here will get ignored after E time of 0. And it will just retain the information that it calculated at the beginning. That's the beauty of a script element, is that it carries its state forward. Like all other GoldSim elements that carry state forward, it has an initial value. That is really the clue for those of you wondering what is a state variable, what is a state, what does that mean? It's an element in GoldSim that can carry forward its value, and it remembers it as it goes forward in time, and it doesn't need to update anymore. It can just stay there static and hold that value. Any element that is asking you for an initial value is going to be that way in GoldSim. Okay, so at time 0, we calculate this thing, and then it just holds that value for the remainder of the simulation. So we don't have to repeat this. This is a very expensive, computation-wise, a very expensive algorithm here, because it's looking at these big time series elements, and it's walking through the time series row by row and calculating things. Anytime you do that, where you go and you reference a time series and index it, or you get a value from a time series. So here's an example. This is the precipitation time series. I am now referencing one value from it. So that's an expensive process. It has to go down through the time series and find, it has to find the time that you're referring to and report its value. And for a very long time series, this can be an expensive calculation. Now we do, under the hood, we do optimize that process of searching for that value. So it is fast, but it's still overall, over the whole simulation, would be very expensive to repeat that. So we don't repeat it. Anyway, I hope that answers your question there. So anyway, that's the script. Okay, so next, we come up with this melt potential and then melt actual. It's depending on how much snow is there. We need to make sure that we don't go over with the amount of snow there that's available. And then if we go open up this reservoir element, you can see that we have an initial snowpack that you can define. Very important, right? Depending on when you start the simulation. And I would like to note, by the way, that when you're dealing with snow, I have found it to be much simpler if you start the simulation in a period of the year in which there's no snow yet, because it's a little bit tricky, right, to set up a model that where there's already snow there. You need to know exactly how much is there right now. If you know that, it's no problem, but if you're not sure, then it would be better to start the simulation when there's zero snow, and then your initial condition could be zero. But anyway, I'm just saying if you start the model, in the wintertime or when there's snow, then obviously this would be non-zero here. Anyway, the reason we're using a reservoir element is not because this is a reservoir, but it's because we're trying to accumulate this quantity of snow and then also take away from it, but never let it go to negative. And a very easy way to prevent it from going negative would be adding a lower bound. However, because the way that we're calculating the melt rate, we're accounting for the snowpack that's there right now. So see how there's a feedback loop here? This feedback loop here, you see it is going from how much snowpack we have into this element called melt potential. So the amount of snowpack that's there is driving what the potential for the melt is. So in this case, I haven't tried it yet, but if you uncheck this box, I don't think we would go negative anyway. But that's what the nice thing about a reservoir is it'll give you a really simple way to never, ever, ever let it go to a negative value as you're going through time there. We don't need an upper bound in our case. Okay, so that's what the reservoir is being used for. The other nice thing about a reservoir is that as opposed to a pool element, the pool element would be something you would use for a real pond or reservoir or tank. The reservoir element is different. It can be defined as a vector. And you can see up here it's a vector of elevation zones. So this is actually accounting for 3 different snowpacks, right, for each zone. And it's all being done without having to have 3 different elements, which is nice. Okay, so that's where we're accounting for the snowpack. Anyway, the rain just drops right through, and then we have this delayed snow melt, and you see it also says average here. We are taking the mean of the 3 different melt rates. Mean V is a built-in function, and then we add those 2 together to get the melt rate. Okay, so that's the melt and rain, which then drives the runoff model. So if I open up the runoff model, again, this is available in our library. It's called the GR4J model. Typically, GR4J includes that snow melt already. I decided for now to have 2 separate models in case you might be working on a watershed that does not have a snow factor in there. Then you don't need that part, but they're very easy to combine. All that you need to do is take the melt plus snow output from this model and then just put that into the P expression here, which is for precipitation. So if you have snow, then take that from the snow melt output If you do not have snow, then this is just going to refer to the precipitation only. Okay, so that's precipitation. The next component is the potential evapotranspiration. Um, I did something that was very simplistic here. So in the interest of time, I didn't have a lot of time, but we do have a model that will allow you to approximate evapotranspiration, and it's called Hargreaves. And oh, I don't have the. I just took the equations from it, but we have evapotranspiration functions. There, most of, I would say, well, I think we have 3 or 4 of them. All but one are very simple. There's another one that is more of physically based, and it's a lot more complicated, and it's used by it's used for the it's called FAO procedure, which I don't want to get into right now, but just know it's a very simplistic representation of calculating evapotranspiration, and it's based on the temperature and the latitude of the site. So with those inputs, then we calculate evapotranspiration, and I'm calling it potential evapotranspiration here. And then I use a splitter to say, okay, depending on whether precipitation is greater than evaporation or not, it depends. If precipitation is greater than evaporation, then we'll take the difference, and then we'll say, okay, that's the net precipitation that is now available to go into the ground or run off. If it's the other way around, if evapotranspiration is greater than precipitation, then we don't. But we still need to account for the water evaporating from the soil as well. So whether or not, just because evapotranspiration might be greater than precip, it doesn't mean we just ignore it. It still needs to be applied. And so that's why you can see here that we have these EN and PN values. That stands for net evapotranspiration and net precipitation. Anyway, so it goes through the splitter, and it's kind of following this diagram that's over here too. The first thing it does is, well, there's 2 things that happens. There's direct runoff that just immediately runs off, and then it gets routed. And then there's the production store. And this is somewhat similar if you're familiar with our AWBM model that we have, somewhat similar to that. But this one uses unit hydrographs. That's the major difference, instead of just using a simple recession runoff function. But the first step is for it to go into what's called a production store. And so there's 2 things fighting this. There's the precipitation that's filling this store, and then there's evapotranspiration that's depleting that store. And there's percolation that is then leaving that store and going into the routing function along with the direct runoff of that. So if I go into the production store, these are the calculations that are used to calculate it. In this case, instead of using a reservoir element, I'm just using an integrator element, just because of simplicity of what the equations are. There really isn't a big reason to go with anything more complicated than an integrator element. It integrates the same way a reservoir does, but it just doesn't have the ability to separate inflows from outflows. But we don't really care. We've just got this really simple equation that we put in for the rate at which it's increasing or decreasing. Anyway, we go through routing hydrographs, so we have these convolution elements for the hydrograph or for the unit hydrographs. And if you look at the diagram over here, you can see these X. Well, maybe it's hard to read on your end, but we have these 4 parameters, and that's why this model is called GR4J. There's X1, X2, X3, X4, and those are driving things like, for example, how much can we store in this production store? That's what X1 drives. What is the shape of the unit hydrograph? That's what X4 is for, etc. And I'm going a little bit too in depth onto this model, so I'll just kind of leave it at that. It goes through those stores and then it calculates total discharge. So that's the model. All right, so let's talk about calibration. So what I want to do is I want to look at what is our total discharge at the downstream end of this watershed, and then let's compare that to the observed records. So let's just first just do that. So I'll run this model. Oh, first let's look at the time frame that we're dealing with. I'm looking at 2004 to 2005, and I picked August 2004 because that's when we are starting off with no snow, and then we'll go through just a period of 1 year. So if I run this model, I do have many years of record, but I'm just focusing on 1 year for now to keep it simple. Um, but here's the outcome, which is not looking good, right? Currently, the total volume is way off, and the peak is way off. Yeah, it's not fitting at all. The blue line is the model discharge, and the observed record is this is the red line there. Okay, so we're way off, and now we're sitting here thinking, okay, now what do I do? And before I go into the automated processes you can use in GoldSim, like optimization, I would say the far and away the most important thing is to come to an understanding of how these models work. If you try to do an optimization without even knowing how the models work or how the input parameters affect the outcome, it's going to be an uphill battle for sure. It is really important to understand just conceptually what these input parameters are doing, and that's why I put this diagram in here and show all these things, because X1, it's important to know that X1 increases the volume of this production store. If you increase that value, then you can imagine that that would have a direct impact on how much water is slowly being released from this store. If you make X1 very small, then you can imagine that it would be spilling over, overflowing, or actually not overflowing, but increasing in over. It's um, it would be probably producing much more in a cumulative sense, much more volume than what is realistic there. Also, if you increase X4, then it would essentially attenuate the hydrograph. You could imagine it kind of spreading longitudinally in time more. So those are the kind of things you should expect from adjusting those. It also gives you an idea of the range of these parameters. You can imagine that X1, you have to think of it as how much water can be storing in the soil profile. So it would give you an idea of, well, it doesn't make sense that it would only be a half of a millimeter, or that it would be 5,000 millimeters, right? It would be something that you would think, okay, this is realistic for a real watershed. So it's important to understand what those parameters are doing. And a really good way to do that would be to use scenarios. Scenarios is always a good thing to use, just for helping you understand these kinds of things. Another one is sensitivity analysis. So I'm going to run through both of those really quick. The sensitivity analysis is a built-in tool in GoldSim that allows you to see the impact of certain input parameters on an outcome. So let me go there, sensitivity analysis. And I already have this set up. I have a thing called objective function, and the objective function is looking at all kinds of statistics of the outcome, the modeled outcome, and it's then comparing it to our observed record. So let me show you some of those examples. I go in here to the calibration, and then we have these different calibration techniques. One of those is Nash-Sutcliffe efficiency, NSE, and then we have some of these others here. I've added a couple of others. One is cumulative error, and one is certain time points, which I'll talk about in a bit. But let's just take one of these for example. So this is a commonly used function to see how close your modeled output fits to an observed record over time. And the reason we have multiple techniques in here is because some are good for certain things and some are good for others. One might be good for low flows, one might be good for finding out what the peak is. And so the nice thing about this calibration container is that we can combine all multiple techniques, and then we can weight them. So if I go up a level, then we have, let me see where I put that, calibration inputs. Here we go. So there's this thing, and this is also contributed by Dave Hoekstra at SRK, by the way, these calibration techniques here. So we can go into this objective weighting element here and then edit data. And you can see that I've weighted all of these equally, but if you're looking at maybe saying, well, I want to see if maybe I'm really interested in the high flows, then you could change this. As long as all of these added up equal 1, then that's the way that we can weight them. There is a check in here that says they don't add up to 1, then it won't let you run the model. Okay, so with all the combination of those techniques, then we have an overall objective function just simply by adding all of those up together, multiplying the objective weighting factors that I just mentioned by the performance matrices, which is just combining all of these factors. Okay, so this is the overall objective, right? We want to maximize this objective function. The closer this value is to 1, the better the performance of the model. Okay, so before we try to start messing with the input parameters to see if we can calibrate this, let's first determine which of the input parameters that our model is even sensitive to. If it's not going to impact the model in a good way for us, or maybe it won't even impact it hardly at all compared to the others, then we should not include it. We should not be trying to adjust it because the more parameters we introduce into the calibration, the more difficult it will become to calibrate. So the first step then is to do a sensitivity analysis, or in the case that I'm looking at, that's the first thing I wanted to do. So I put in our objective function here. This is the result I want to analyze. And then I just put in a bunch of factors here to just see how do they impact the outcome of the model. And so what you do is you put in an input parameter, in this case, degree day factor. And then I put a lower bound, central bound, upper bound to see how this impacts the objective function. So to see how this one parameter impacts the outcome, just this one, with all the others being held constant, then I click this plot button over here. And then what it will do is it will run through a bunch of runs and then come up with this plot. This one, let me make this a little bit smaller. And it shows you how the objective function is changing as we change the degree days. So you can see here that with a high degree day factor, we're getting a very low objective function. But also, not only that, we're getting a wide range here. So the objective function is going to range between 0 and 1. And so you can see here that the model is being greatly impacted by that input parameter. If we do it again for, let's say, KC, this is to calculate evapotranspiration. So I'll run it again. And here you see that it is also impacting it, but mostly in a negative way. The number at the beginning here, the highest value is not even 0.5. 0.5 would be not a good calibration, right? So it's just getting worse as we change this value. So that is, these kinds of things it's giving us a clue as to where we want to be, what we want to be looking at. Here's the X1, and the X1 is showing that it's low, it rises up, and then it starts to drop. And this is a good indicator of kind of the range where we want to be looking at for our calibration. We probably want to stay in the range between 200 and 400, or maybe a little higher. The reason we can't just pinpoint one number is because we're holding everything else constant, right? And so it really requires a combination of multiple inputs to help with a calibration. So we can't just immediately say, oh, it's going to be this value. We need to set this at 300 because it can shift depending on what other input parameters are doing. So that's something to keep in mind. The sensitivity analysis is really just telling us how sensitive is this output to these input parameters. It's not really telling us a whole lot more than that, but it is it is going to point us to the 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 inputs that are of the most importance here, the ones that the model that we should be looking at first, to help us zero in on keeping the number of input parameters as small as possible, the number of them. Another good analysis is a tornado chart, and that's going to look at all of these input parameters together on a normalized scale. So we'll click on this, and we get this plot here. So this is showing us different inputs as in order of how much they impact the outcome, and you can see that the one down here at the bottom is having relatively very small impact on the outcome. So this would tell us that we'd probably want to eliminate this input from our calibration. Okay, so there are some other results that you can look at that are helpful, but that's essentially what a sensitivity analysis can do. Probably a good idea to run that before going through the calibration. Okay, so the next step is to do the optimization. So I'll go up here to run and then optimization. And what I want to do here is I want to maximize our objective function. So I'll change this to maximize, and then I'll click on the, I'll go find the objective function. There it is. So I want to maximize that, and then I'll add our parameters here. So I'll just put ranges here, say 600, and then maybe put the central point at 200. This is not the central point, this is the initial value. So it's kind of it's going to hunt for a good combination of these parameters, but it needs to start with some value. So I'll just assign it a value that's kind of in the middle on all of these. And all right, we're almost there. X4. I'll put one more in. That's the degree day. Oops, that's in the melt rate. Okay, so now that we have all those entered, I'll click optimize, and so let's see, the best that it could find was a 0.65, which isn't really great, but what we can do is we can close this, and then when we close the optimization, then we can copy the values that it found and put those into the input definitions. So I'll close that and then run it with those input definitions reset to see how that impacted the calibration. So you can see here that it has improved significantly from where it was before, but still not very good right there. So it might be a good time to start trying to figure out how do these input parameters affect the outcome. And a good way to do that is with the scenario analysis. So scenario analysis is this little icon with these three lines and these little colors right up here. I am using a newer version of GoldSim that is set to be released. That's next. It's going to be GoldSim 15. And so that's what I'm currently using. It has much of the features that we've been working on over the last year in here. Plus there will be more. But anyway, what we can do now is we can say, well, let's run 3 different scenarios, and let's just change one of the input parameters and see how that impacts things. Let's start with this x3 factor. So I put in the same thing. I put in x3 for scenario 1. I gave it a low number, scenario 2 kind of a mid, and scenario 3 a higher number. Let's just see what that does to our hydrograph. So I'll run all of these scenarios, close, and then open up the same chart again. And I want to see, instead of just the observed record, I want to see everything combined, all the different results plus the observed record. So the observed record is red, and then our modeled results are in blue. And so you can see here that it makes sense that we want to avoid whatever's going on here with these big spikes, right? And so if we look down into the legend, we see that that is scenario 1, these big spikes. So we could go back to our scenario manager and say, well, what was scenario 1? Okay, that's a low value. We want to stay away from the low values. We can see here that the low value is causing, this, and so therefore let's stay away from that. So what I'm saying here is it's giving us insight more than the sensitivity analysis, right? The sensitivity analysis is telling us one thing. It's saying, the model is very sensitive. That's all it's telling us. It's kind of not revealing a lot to us. But we can see here that as we adjust that number, that we can see the whole picture. We can see how the whole shape is changing. So that's how scenario analysis can be very useful. We could do another one, another results, and I would recommend initially doing just one at a time. Otherwise, it gets too complicated. But let's look at another one. So let's see. We could say, I can't remember which one we did before, but I can't remember if it was X1. Was it X1 or X2? Well, I don't remember, but anyway, that's a really good way to understand the impact. If you're just trying to understand how the model works and how these parameters affect the model, a really good way is to use the scenario manager there. So anyway, let me continue through this optimization process. I think one of the things that I wanted to look at actually is the X3 and the X4. So X3 is capacity, X1 is capacity. Those are parameters that it would make sense to have these be potentially, quite a larger range than the others. So X1 and X3. And I think in my optimization, I had X2 as a large range, and I don't think we want to do that. So I'm going to change this to just 2 to 40. And that might make it a bit easier for the optimizer. So let's try this again. And you can see that already, immediately, right off the bat, I didn't change anything else. All I did was change the range of that one parameter. And I found that just by kind of getting a little bit of insight from how the model works, I looked at that graphic and I determined that I don't want X3 to have a very large, sorry, did I say X3? X2 to have a large range. I shortened that range, and you can see that we immediately got a better calibration. We went from 0.6 all the way up to 0.8 in our objective function. So now I'm going to definitely check these 2 boxes. I want to save those values where it ended up for the next optimization that I run. And in addition to that, I want to copy the outcomes into those input parameters, which is what the second checkbox does. So it says right here, replace element definition with the optimized value. So now I'll run this again and open up the chart. And you can see that it's starting to look better. Still not perfect. We're quite a ways away from the peak still, but you can see that from where we started to where we are now is a significant improvement. And so we could go on here, but the hour's up, and so I hope that this has been useful for you, and Mostly I just wanted you to be aware of the techniques that I'm using, sensitivity analysis, scenario manager, and the optimization. One other thing that somebody asked on Tuesday was, well, what can I just look at a certain point on the hydrograph, a certain point in time? So an example would be in this chart we're looking at right here. What about just looking at this peak and saying, I want to approximate that value, or maybe you pick 4 points. Maybe you pick the bends. You could say, I want to pick a low flow point. I want to pick the inflection point here where it starts to rise, and I want to pick the peak and then down here. You can do that with discrete changes. And so let me show you that. I didn't implement it into the objective function, but if you go into the calibration techniques, then I have this one called time points. So you can use discrete changes. Whoops, I need to move that over. You can use discrete changes to pick a point. So I just have 1 point here. I think there would be a smarter way to do it than just saying, here's a date, I want you to just use this value. What I did is I said, okay, I knew the peak occurred at this point in time, so let's just assign a date here and then say, tell the model to grab the value from observed record and from the model at exactly that point in time, put it into an integrator so that we have it at the end of the simulation, and say that's the difference between those two is our peak error, you could say. So this is the time to peak. Actually, the better thing here would be peak date. So you could imagine you have multiples of these looking at different points, inflection points on the hydrograph, and then you could calculate the differences between those. So that's a way to do it. You could also use an extrema element, right, which captures the maximum value that it occurred. That would be a smarter way to capture the peak. But if a brute force way to do it here is just to simply specify the dates that you see on the observed record. I also looked at cumulative, so this is looking at the total cumulative flow, and then just to make sure that for mass balance purposes that we're not creating more water than what was observed flowing through that gauge. There are others, and the point is that you can just build on what is here, to add different performance functions to the calibration. Anyway, that is what I wanted to show today, and I'll wait around here for if you have any other questions. Thank you for joining, and hopefully we'll see you next month.